Hello and welcome to this lecture. So we've been studying how to solve linear equations first, and then we studied linear transformations and how the left hand side part of the equation, when you have a lot of equations involving a lot of variables, is actually doing a linear transformation on a vector, right? So and then we studied theoretical properties of the linear transformation, range, null, and what it all means, how to visualize it, etc., etc. Now we're going to put the two together. We're going to take the theory of linear transformations that we learnt, and we're going to look at the method we employ for solving linear equations and try and match the two and make some statements based on range, null, about solutions of linear equations. Okay, so that's the main part of this lecture. So let's get started. As usual, we'll start with some examples. We'll see a few examples. We'll look at what can happen and then put it into a larger theoretical framework. Okay, that's going to be our idea. So here is a very simple example: 3 variables, 3 equations, and we know how this is solved. We are going to eliminate, and then we end up with a unique solution. So you can see for this particular set of 3 equations in the 3 variables, you can do an elimination here, one more elimination that gives you z, and then from there y, from there x, and you get a unique solution which we call as a dimension 0 solution. We've been looking at how this relates to the column space and other things. We will see that a little bit more in detail. Okay, so now in terms of the linear transformation involved here is represented by this matrix, where every column is a column here, right? So 1, 1, 1, 1, 2, 2, 1, 3, 6. So this matrix represents the linear transformation. If you want to think of the column space or range of this linear transformation, you have to look at the span of the columns, right? Remember, this is a span of the columns. So span of 1, 1, 1, right, written this way, and then 1, 2, 2, and then 1, 3, 6. Okay, so to figure out the span of this, see, one of the things we do is to go towards this row reduced form in elimination, right, and that gives you a better basis, right? It gives you a simpler basis in which things like membership and all of those are easy to solve. So this is very important. So we'll do that first. So for that we need to do elimination and all that. But if you notice, this if you want to put together one row below the other is not actually A, right? A has, columns and rows are swapped, right? So you have 1, 1, 1 here, that's okay, but then 1, 2, 2 is actually the second column here that is showing up as the second row here, etc. Okay, so this row column swap of a matrix has a name, and that's called transpose. Okay, so this is the first time maybe in this class we're seeing this transpose, a transpose of A. So you have a matrix like this. What is the transpose? The first row here becomes the first column here. The second row here in A transpose becomes the second column here. The third row in A transpose becomes the third row here. So in this particular case, it becomes something like this. So once you have A transpose like this, now you have all the columns lining up as rows, and you can do your row reduction or elimination as before. So if you do that, if you do the RREF for this A transpose, you will end up with a 1, 1, 1, 0, 0, 0, 0, 0, 0 elsewhere. Okay, so this tells you that the column space is actually spanned by not just the space spanned by 1, 1, 1, 1, 2, 2, 1, 3, 6 is actually the space spanned by 1, 0, 0, 0, 1, 0, 0, 0, 1. Look at how easy it is. So RREF, as we know, is very, very powerful. It gives you a very simple basis for the original span that you have. This may be very complicated. This one becomes really, really easy. So in particular, we can see the span of these 3 vectors is nothing but R3, isn't it? The entire 3-dimensional space. So the rank of this matrix is 3. The range ends up, which is the column space, ends up being the entire R3. So I'll use range and column space interchangeably so on from here on. Okay, so the range is the entire R3, and now from here you can quickly figure out that that the nullity is 0, and the null is actually only the 0. Okay, so you can see this matrix is full rank, and only the all 0 vector will send Ax equals 0 will only happen when x is equal to 0. Okay, so this is an important thing. Okay, so this is the first thing you have to do. So anytime you want to understand a little bit more about the linear equation in terms of the linear transformation that is contained in it, you have to first understand the linear transformation. How do you understand the linear transformation? You have to understand its range and null. Okay, so the range and null in most cases, small cases like this, or even big cases, you can do it by computer. You can do an RREF on the A transpose to figure out the column space and the null, I think dimension of the null space, right. So this is the first step, and in this particular case the null space ended up being 0, so we don't need to find the basis of the null space. Later on we will see examples where we have to find the basis of the null space. There you have to do a little bit more, so I will show you what you have to do at that point. Okay. So this is all I wanted to say in the beginning. Now we are going to take this and put it into a nice diagram, sort of a visualization of what the linear transformation is doing. So this is an important sort of picture. This is the linear transformation view of the linear equation. So notice now in this equation I am making the right hand side as arbitrary. Okay, so I am making it r, s and t. Some r, some s, some t. Okay. So if you do this, you can solve, right. So even if it is r, s and t, even if it is not a particular value, you can do the elimination, right. You can subtract, you will get some s minus r, t minus r, and then t minus s, etc. You will finally get to a solution like this. Okay, so it's easy to solve. You just do the same algebra here, you will get some solution like this. Okay. So this is again a dimension 0 solution, and it's a unique solution. We know that that's true. Now I'm going to take this picture and sort of represent it on some diagrams, and then get a visualization of how the linear transformation is working. Okay. So this is what I'll do. My matrix again, this is the matrix that represents the linear transformation, and my transformation is from R3 to R3. Now I'm going to represent R3 with these ellipses. This is roughly, just to get a picture of what's going on. So all the points of R3 are here, and here are also all the points of R3. My linear transformation T from R3 to R3 represented by A takes a point in R3 and sends it to a point in R3. Okay, so that's what I'm going to represent here. Now I know from my previous calculation that the range is the entire R3 and it's got dimension 3. So if I take my T and act on every single vector in R3, that's going to take me to the entire R3. Okay, right, entire R3. So every point here goes to a point here, every point here you can come from some point here. So it's one of those one-to-one mappings, isn't it? This transformation works like that. I know that my null as dimension 0, it's only one point, right? It's the all 0 point, the origin alone, 0, 0, 0 is the only point which will take me to 0 here, right? So from null, if I go through T, I'm going to go to 0, right? So that's what's going on. So how do you picture this? How do you get a high level view instead of, so of course from the equation you can do all the calculations and go to the solution every time, but I want a high level view, right? So in the high level view, what's going on is, if you pick any right hand side, any point here, you can go back to a unique solution, and from that point you can come here. So this happens because of the one-to-one nature of this mapping. Okay. So this is just a representation of what's going on. So we'll see as we go along. So basically you get a unique solution for any RHS. And so at this point, I don't know if you want to call a name for this diagram. One of my colleagues calls it the tabla or a mirdangam type diagram. So we're going to make more and more of these tabla and mirdangam type diagrams to represent these linear transformations, and sort of talk about the representation and the linear equation together and get a sense of what's going on. Okay. So if you see here, both of these represent the same thing, the general linear equation also represents the same thing, but except the linear transformation seems to give you a slightly more abstract picture. So you get a better understanding without going into great solutions. You get an understanding of what's going on. Okay. So we're going to see more examples. You'll see as we see more examples, this picture will start getting a little bit more complicated. Okay. So the mirdangam, which is so symmetric and sort of nice here, will start losing shape a little bit. It will start looking a bit different. And as we go forward, let's keep looking at it. Okay. Here is the next example. So in this example, I've cooked up an example for which, even though you have 3 variables, 3 equations, there are infinitely many solutions. Okay. So this can happen when the rank is not full. Okay, when the rank is not 3. So that we can check. We have A, which is 1, 1, 1, 1, 2, 4, 1, 3, 7, and then we look at A transpose, right? So we need to do A transpose to figure out the column space. And if you do the RREF, lo and behold, you see there is a first row which is non-zero, second row which is non-zero, third row becomes 0. So you can check this very easily. This RREF is very easy to do, the elimination, and you see that this matrix is a rank 2 matrix now. Okay. So the range is not the entire R3, it is a 2-dimensional subspace of R3. Okay. So range is a span of 1, 0, minus 2 and 0, 1, 3, and it's got dimension 2. Okay. So this is range. Now when range has dimension 2, by your fundamental theorem, you know that the null space has dimension 1. So now I have to find the null space. So how do I find the null space, or how do I find a good basis for the null space? Here is what you have to do. This is how you compute the null space basis. You have the matrix A. I need a null space vector. Let's say the null space vector is k1, k2, k3, some arbitrary vector here. A times the null space vector has to be 0, right? I have to basically solve this equation. It's also like a linear equation solving, except that the equation is homogeneous. What's called homogeneous? Homogeneous is if the right hand side is all 0, and that such equations are called homogeneous equations. So these homogeneous equations have different types of solutions, and for that it's important to do RREF on A. Okay, so you remember for the column space basis we did an RREF on A transpose to get a simple basis. To get the null space basis, we are going to do an RREF on A. Okay, on A itself. So if you do a row reduction here to solve this, you have to just do elimination on A. So that's what we are doing here, and you end up getting the row reduced form to be 1 0 minus 1 0 1 2 0 0 0. We already know the nullity is 1. If you didn't know, from here also you can figure out that the nullity is 1, right? You see that the rank of A is 2. From there you get nullity to be 1. Okay, so this is the picture that we're going to work with. So from the RREF, how do I go towards null space basis, right? So now I want basically the same k1, k2, k3 carries over here with the RREF of A. k1, k2, k3 should give me 0 0 0. This is what I want. Okay, the trick is to identify free variables and dependent variables, right? So in this form we know already that this guy, the variable corresponding to this last column, is free, and these two other variables are dependent, right? So k3 is a free variable, k1 and k2 are dependent variables. So to find the null basis, there is only one free variable, and you can set that free variable to 1. Okay, basically when there are multiple free variables you have to do multiple things here, but right now we have only one free variable. Later on we'll see some examples with multiple variables and all that, but here we have only one free variable, so you simply set k3 equal to 1. If you set k3 equal to 1, you can solve from here and find out when k3 is 1, k2 has to be minus 2. Okay, only then this second equation will be solved, and then k1 has to be 1, right? So when k3 is 1, you can go ahead and solve for k2 and k1, and you see that you got a k1, k2, k3. This is a basis vector for the null space. Okay, so null of T is the span of this 1, 2, 1, minus 2, 1, and it's got a dimension 1. Okay, so this method is important to understand. It's basically solving a linear equation like this, right? And you have to do the row reduction on A, and then put a value of free variable to be 1, and then solve for the remaining dependent variables. You get a basis. When the null space dimension is 1, this will work. Okay, when the null space dimension is 2, you have to put two values for the true free variables. Usually you put the canonical basis. You put 1 0 and 0 1, and then solve for the remaining. Okay, so we'll see some example of that later on. So this is how you find the null space basis. So now for my equation that I'm trying to understand in a more abstract way in terms of linear transformation, I have the matrix which represents the linear transformation. I know the column space, I know the range, it's a two-dimensional subspace, I know the basis for it. I know the null space, which is a span of 1 minus 2 1. So I'm going to put together a picture of the linear transformation view. Okay, so here is the picture. This is my equation. I've only shown the left hand side because the left hand side of the equation is what controls the linear transformation, isn't it? So the left hand side is shown here. This gives me the matrix, and with this itself I have I can compute all these information, right? I know that my linear transformation is from R3 to R3, so I have my ellipses as before, but then I know that my range is only dimension 2. What is my dimension 2? It's got a span of 1 0 minus 2 and 0 1 3, right? So 1 0 minus 2 times R plus 0 1 3 times S. This is any point in the range. And now this has got only dimension 2. So I put a smaller ellipse there, and I've shaded it with this orange yellowish sort of color, and then that is your range. Okay, so you see the range is not the entire R3. So if you take this transformation T and then give input as all possible R3, you won't go to the entire R3 here. You will only go to a subset, which is the range, and that's what this is showing. So you can see the tabla or mridangam, whatever, is getting a little distorted, right? So it's not the full shape, it's getting a little distorted, and that tends to happen when the matrix doesn't have full rank. Not only that, here is another interesting part. The null space is not just a single point. It's not dimension 0, it's got dimension 1. So the null space is a line, so to speak. It's some set of points here, and that's basically all multiples of 1 minus 2, 1. So what does the null space do? Any point in the null space, when t hits it, gets mapped to 0. Okay, so all these guys under t go only to 0. Okay, so I have not shown that explicitly here, it just clutters the picture too much. So all these points go to 0. Okay, so that's why you see this entire R3 has many points going to only one point. Okay, so it's a many to one map in this particular case. Okay, so let's dig a little bit more deeply into what we can do. First, I'm going to pick an RHS which is in the range. Okay, how do I pick an RHS in the range? Basically, multiply this by R, multiply this by S, and put the values here. So you see the first coordinate is R, second coordinate is S, third coordinate is minus 2R plus 3S. So if I pick my three right hand side values to be in the range R, S, and minus 2R plus 3S, what do I know? When the value is in the range, I should get a solution, right? So you can try and solve. Now you know how to solve, right? You can do elimination and solve. So you write down this equation, subtract, eliminate, and solve. If you do that, you will see that you will get solutions like this. Okay, so you will have a free variable z, and you'll have to pick your z to be u, and then in terms of u, you can solve for the equation. So that if you split up, you will get one vector here, 2r minus s minus r 0, plus something 1 minus 2 1 multiplied by u. And notice how miraculously this 1 minus 2 1 is the same as the 1 minus 2 1 here. Okay, this is not an accident. We will later on see a very nice abstract result which guarantees that something like this will happen. Okay, so this null space ends showing up in the solution. Even in the previous case, it actually showed up, but the null space in that case was only 0 0 0. So no point in adding it. In this particular case, the null space is non-trivial, so it ends up showing up here. So this is a very interesting fact. So when you have the right hand side in the range, even when the range has lesser dimension, you end up having infinitely many solutions like this, right? So you see here, all these guys which are in this white extended narrow ellipse here, all of those guys go exactly to this one particular vector. Okay, so this is a very interesting type of picture here, and we're going to draw more and more interesting this tabla style pictures, and you'll see interesting conclusions happen. So infinite solutions for RHS in range of t. So notice this connection here. So you have a linear equation. You've been always thinking of it as linear equation. Now we are taking a more abstract view. We're looking at the underlying linear transformation, and we're picturing that linear transformation and thinking of it as an entire object. How does it behave? Okay. So let's see more examples. The other immediate example to see is the same equation, except that the right hand side is chosen outside of the range. Okay. So I'm going to pick R, S, and the third value t, and the t I will make sure is not equal to minus 2r plus 3s. So in that case, I will not be inside the range. I would have gone outside the range. When I go outside the range, there will be no solution. Okay. So there is no way I can go with t hit on any point here. No point here will ever take me to that point. Okay. So this is a case when you have no solutions. When you have an arbitrary r and s and t not equal to minus 2r plus 3s, you will not get a solution for this linear equation. So notice how interesting things we're able to understand and observe when you view the linear transformation as a whole and think of it in this tabla fashion and see which is the point in the range, which is not in the point in the range, etc., etc. Okay. So this I hope is interesting. We'll see a few more examples to make sure that we understand the idea very clearly. But for this lecture, let's stop at this point and pick up from here in the next one. Thank you.